Welcome to this lecture. This is the first lecture of week 5. In the previous lectures of the previous week, what we have looked at are convergences of random variables, and then we have been looking at convergence of series of random variables. In particular, we have concentrated on probabilistic methods of ensuring almost sure convergence of a series of independent random variables, and there we had looked at important inequalities like the Kolmogorov's inequality and the Etemades inequality. These inequalities essentially tries to get estimates for the associated sequence of partial sums. We have also discussed the 0-1 laws, where we have commented on the fact that if you are starting off with a sequence of independent random variables, then the corresponding series of random variables will either converge almost surely or will not converge almost surely. So, that was one of the facts that we have obtained from the 0-1 laws, which connects to the properties of a tail sigma field that we had discussed in the previous lectures. In this lecture, what we are going to look at are additional conditions on top of independence, which will ensure the almost sure convergence. So, without further delay, let us continue discussing with the lecture notes. So, we are setting things up again. So, we are working with some specific probability space, and we are given a sequence of random variables, all of which are given to be independent. And now, we have already seen that the set of points or the event where the convergence happens is either 0 or 1, and we are now interested in sufficient conditions which will ensure that the probability is actually exactly 1. Towards this direction, this is our first important observation, that we start with this independent sequence of random variables, but assume this integrability that all of these are coming from the L2 space, meaning their second moments always exist. But remember, as long as this happens for all n, then in particular the first absolute moments and the first moments exist, and moreover the variances are also exist. So, for all n we can work with the expectations as well as the variances of this sequence of random variables. Now, the conditions will now be in terms of variance of x n's and in terms of the expected value of x n's. So, we are using the fact that variance of x n as well as the expected value of x n, all of which are finite for each n. Now, here the criteria says that we have to look at this series of real numbers. In particular, note that the variance of a random variable by construction is non-negative. So, we are looking at a series of non-negative real numbers, and we are asking for the convergence of this series. So, that is the condition we put as part of the hypothesis, and the conclusion says that the centered random variables, which are x n minus expected value of x n, centered because their expectation is now 0. So, these centered random variables, if you sum them up, then the corresponding series must converge almost surely. So, the condition is in terms of the variances, and that ensures that the centered random variables, if you look at the corresponding series, they converge almost surely. Alright, so let us try to see the proof of this result. So, what we do? We introduce certain notations which will make our argument easier. So, we are going to look at these centered random variables and call them as y n. But now, we are interested in the convergence of the series summation y n, and now as expected we would also like to look at the convergence of the associated sequence of partial sums, which are given by these random variables s n, defined in the way that it is the sum of first n many random variables 1 up to y n. Now, we are interested in looking at the sequence of partial sums, but now note first that the expected value of y n is 0, because we have already centered them, and hence the finite sum which is s n, which will also have the expected value 0. So, all of these has mean 0, but now moreover you also note that shifting a random variable by some appropriate constant does not change the variance. So, variance of x n matches with variance of y n, that happens for all n, and as a consequence, if we use the independence of the structure, then we observe that as long as x n's are independent, so are y n's, because we have only subtracted certain constant from the x n's, and therefore, as long as x n's are given to be independent, so are y n's. But then as a consequence, since S n is a finite sum of independent random variables, then the variance of S n must also be the sum of the individual variances. But here we are working with variances of y m which are same as variance of x m, and that is what it becomes, that the variance of S n is given to be the sum of first n many variances of x m's. All right. So, now we are interested in the almost sure convergence of this series of centered random variables. Now, note that as per our notation that we have introduced, we are looking at the almost sure convergence of the series given by y n's. So, we are looking at summation over y n's, but then y n's converge almost surely if the corresponding sequence of partial sums converge almost surely. But we had discussed this earlier in week 3, that there is a corresponding Cauchy property that characterizes the convergence almost surely, and that is this fact that for all epsilon positive, if you look at this event where terms coming from the jth summation and the kth summation, they differ by more than epsilon. If you look at such events over j and k greater or equals to n, the probability of such things happening will go to 0 as n goes to infinity. So, in the limit these probabilities go to 0 for all epsilon positive. So, this is some kind of a Cauchy behavior that we have pointed out earlier in week 3. So, please go back and check. But this condition that we have recalled can be restated in this formulation, that for all epsilon positive, if you start to look at the differences of such sequence of partial sums starting with S n and the remaining terms. All right. So, we are looking at S n and then any subsequent S n plus k. So, we are varying the values of k from 1 to infinity, and we are looking at all the subsequent partial sums. Now, if these quantities greater or equals to epsilon, that event happens with very small probabilities, in the sense that the probability of these goes to 0 as n goes to infinity, then the same condition holds. So, this is essentially a restatement of the Cauchy property corresponding to the almost sure convergence that we are looking at. Now, what we are going to show is that this relation, which we denoted by star, actually holds under our assumption. Now, recall that we are using the fact that the x n's are given to be independent, and therefore, we can appeal to the Kolmogorov's inequality, which we have discussed earlier in the previous week. So, this was theorem 5. Please go back and check. So, here what we observe is that if we look at this probability, which we want to show that goes to 0 as n goes to infinity, has this interesting reformulations. So, we simplify this probability in the sense that we look at the union of first m many such events, but as m goes to infinity, these events increase to the complete union over k equal to 1 to infinity, and therefore, by the continuity property of the underlying probability measure, we end up having the limit of these probabilities involving finite many unions. But now, when we are looking at this finite union, that can be described alternatively in this sense. If we are looking at this finite union, here we are looking at these random variables, and we are looking at the union of the events in each of which the random variables are exceeding epsilon. That simply means that the maximum of the random variables must be exceeding epsilon. So, this is a reformulation of the same event in question, but then we rewrite in terms of the this probability in terms of the maximum now. But now again we have simply rewritten the probability of this event in terms of this maximum involving these random variables, and therefore, nothing else changes outside. We continue to carry the limit as m goes to infinity outside. But now, here is where we are going to appeal to the Kolmogorov's inequality, and we are going to say that the probability of this maximum of the quantities will be dominated from above by the variance of the final random variable, which is S n plus m minus S n, the variance of that divided by epsilon squared. So, here is where we are appealing to the Kolmogorov inequality. But remember, we still have a limit quantity written outside, and a priori we are not sure if the limit m going to infinity for this quantity exists or not, but certainly the lim sup does. So, therefore, the earlier limit in the previous step that we are looking at has upper bound given by 1 over epsilon squared lim sup of these variances. So, this is the application of the Kolmogorov's inequality. But now observe that the random variable that we are looking at, which is this difference of these two partial sums, then here what we are looking at are the sum of m many independent random variables y n plus 1 up to y n plus m. Now, here since these random variables are independent, therefore, the variance is nothing but the sum of the variances, and now we go back to the earlier observation that variances of y n is same as variances of x n. So, that is what we write, but now we are looking at lim sup as m goes to infinity of the finite sum of these variances. But now here we are starting with these terms n plus k, and k is going from 1 to m, and then finally m goes to infinity. Therefore, this lim sup is actually a full limit which will be looking at this summation of the variances, but starting with the stage n plus 1. So, we simply re-index the things in terms of k going from n plus 1 to infinity. But now, what is happening is that this is the tail part of the complete series that we are given, which is the variance of x n series, and as long as we assume that this series converges, then the tail must go to 0 as n goes to infinity, and therefore, what we ended up having is that the term that we have started estimating, which is this quantity, goes to 0 as n goes to infinity. But this was exactly the reformulation that was described in the relation star earlier, and therefore, by going back to this star relation, we conclude that this must converge almost surely. That gives us the first important result in this direction. So, we are looking at a sequence of random variables coming from L 2, and we are also assuming the independence. Now, if the series formed by the variance of these random variables converge, then as a consequence we have proved that the centered random variables x n minus expected x n, that series must converge almost surely. But now, a quick consequence of this result will give us the next result, which is typically referred to as the two series theorem. So, this is a straightforward consequence of the earlier result, and we state it as a corollary, but this is typically referred to as a two series theorem. What we are looking at is again a sequence of random variables in L 2 p, and such that the expected value that series converges as well as the series formed by variances converges. In addition, of course, all these random variables are always assumed to be independent. But now, if we assume that these two series of real numbers converge, then the conclusion is that the series of random variables that must converge almost surely. So, here this result is called the two series theorem, because we are going back to two specific sequence of real numbers which is formed by the expectations and the variances, and then corresponding to those real valued sequences we are looking at the corresponding series. As long as these two series of real numbers converge, then we are claiming that the corresponding series of random variables converge almost surely. So, that is immediate, because as long as you have the variances series converge, you have the summation over x n minus expected x n that converges, but if you add to that the series of expected x n, you get the result for free. So, this is the immediate consequence of the previous result, but this has very nice applications that we are going to see right now. So, let us say we are going to look at a sequence of random variables which are given to be IID, meaning independent and identically distributed. Moreover, we are going to look at a specific structure of these random variables in terms of their common distribution. So, we assume that x n's take value plus or minus 1 with equal probability. So, we can simply think of as tossing a fair coin, which will essentially give you heads or tails with equal probability half. But then if you get heads, you assign the value 1, if you get tail, you assign the value minus 1. So, therefore, if you keep on tossing a fair coin repeatedly, you end up with a sequence of numbers plus 1s or minus 1s, and this is essentially going to give you such a IID sequence of random variables. So, now if you keep on tossing this coin and construct this sequence, then look at this scaled version of this sequence. Here we take y n's to be x n over n. Now, here what happens is that expected value of y n is nothing but 1 over n times expected value of x n, but since x n takes plus or minus 1 with equal probability, expected value of x n is 0. So, therefore, y n also has mean 0. Moreover, we can also compute the variance of y n. So, that is nothing but 1 over n squared times variance of x n. But now, let us compute the variance of x n, which is by property of variances we can rewrite using this form, that it is the second moment of x n minus the first moment squared, but the first moment is 0. So, we do not need to compute it separately. So, now what happens to the expected value of x n squared? You see x n takes the value plus or minus 1, and therefore, the square of x n takes the value 1 with full probability. So, therefore, expected x n squared is nothing but 1. So, therefore, variance of y n is actually 1 over n squared. Now, if you use this observation, then observe immediately that expected value of y n, if you construct a series, that converges because all the terms are 0. Again, variance of y n is 1 over n squared. So, therefore, that series also converges. So, therefore, we claim that summation y n that must converge almost surely, and that essentially gives you the series formed by x n over n must converge almost surely. So, this is a straightforward application of the two series theorem. All right. Now, I give you as an exercise a generalization of this example. So, here what we do is that we look at a sequence of real numbers such that they are square summable, meaning if you look at a n squared, then sum it up, that will converge. Now, if you look at this square summable series and consider the x n's as considered in earlier example, meaning these are IID random variables taking value plus or minus 1 with equal probability, then you can try to show that if you look at these scaled random variables a n x n, then the corresponding series must converge almost surely. So, this is a generalization of the example that we have already discussed. Please work this out. All right. Now, we make a important observation which will be useful in generalizing the two series theorem that we have discussed. So, what we do? We start with any random variable x and look at any positive constant c. We now look at a kind of a cutoff version of this random variable. This is also called a truncation. What we look at is x superscript c. That random variable is defined to be x times the indicator of mod x less equals to c. In simple terms, what it means is that you pick up any sample point small omega and look at the value x of omega. If mod of x of omega is less equal to c, then assign the value x of omega to this truncated random variable. Otherwise, if mod of x of omega exceeds c, you assign the value 0. That is how this truncated random variable is getting defined. Now, note that by construction, for all points the x truncated at c, the modulus value of that is dominated by c. So, here whenever the value of mod of capital X exceeds c, there we are assigning the new value as 0. So, therefore, it is certainly less than c, and of course, in the other case it is matching with x, and in that case automatically it will have the bound given by c. So, therefore, since for all points the truncated random variable has this property, so therefore, probability of that is 1. Now, therefore, what we end up having is that this truncated random variable is actually bounded by c. Essentially, the modulus of the random variable is bounded by c. In particular, since this is a bounded random variable, all its moments exist. but the original random variable, the general random variable capital X that we are working with may not have this property that all the moments exist. In fact, the expectation of x might not even exist, but the truncated random variables, since by construction it is always bounded by a constant c. So, therefore, it will have all moments, and we are going to use this specific fact in order to generalize the two series theorem that we have discussed earlier. And this leads us to a important reformulation, which is essentially helping us dropping the integrability assumption that we have been discussing so far. So far we have assumed that all the random variables are in L2, meaning they have expectation as well as variances, but now we are going to drop that assumption of integrability, but continue with the independence assumption, but instead we are going to look at certain properties involving truncations, and that is going to lead us to this very important theorem, which is called the Kolmogorov's 3 series theorem. So, the result is like this, that you work with a sequence of independent random variables, and we want to say that as long as the corresponding series converges almost surely, then necessarily we will have the convergence of 3 specific series of real numbers. The first is constructed with the probability of the events where modulus of x n exceeds c. So, that is the first series. The second series is made up of expectation of the truncated random variables, and the third series is made up of variances of these truncated random variables. Remember, the truncated random variables have all moments, in particular it will have expectations as well as variances. Now, what we claim is that as long as the original series of random variables, independent random variables converge almost surely, then we must have these 3 real valued series, these 3 must converge for all values of c positive. So, this is a necessary condition. Conversely, the theorem states that if these 3 series that we have described right now converge for some c, it need not be for all c, but if it converge for some c, then the series formed by the random variables must converge almost surely. So, in fact, what we have essentially showed is that it is enough to have the corresponding 3 series converging to have the almost sure convergence of the corresponding series of random variables, and this is important because we have constructed the conditions in terms of 3 series of real numbers, which ideally will be easier to verify. Now, let us consider the proof of this result. In fact, what we are going to discuss is the converse part only, meaning the sufficiency part, meaning we are going to say that if for some c the 3 series converges, then the series of random variables must converge almost surely. In a later lecture, we will come back to the proof of necessity, meaning if the series of random variables converge almost surely, then the automatically for all c positive the 3 real valued series must converge. So, that necessity part we shall discuss in a later lecture. Now, we look at the proof of the sufficiency part. So, here to start off with, we leave you an important exercise, please work this out. So, let us consider these tail probabilities here. So, we are looking at modulus of x n exceeding c, that probability, and suppose this series converges for some c. So, this is part of the assumption of the sufficient conditions that we are looking at. Now, what we observe is that if this series converges, then using Borel-Cantelli lemma, what can be shown is that the event where x n does not match with the truncated random variable, if this happens infinitely often, that event is actually the limb soup of the events that modulus of x n exceeds c. Remember, modulus of x n exceeds c is the event where x n is not matching with the truncated random variable, because the truncated random variable is taking the value 0. So, therefore, this infinitely often event is actually a limb soup of these events, all right. But then by the Borel-Cantelli lemma, please show that the limb soup of these events must have probability 0. Please check this. Now, we go on to the looking at the sufficiency part, and this is where we are going to use this exercise. So, here as long as we use exercise 2, we end up with the fact that there exists some set coming from the sigma field with probability 0, such that on the complement of that set we must have that x n matching with the truncated random variable after a certain stage. Remember, the exercise told us that the x n does not match with the truncated random variable infinitely often, must have probability 0. So, therefore, what it means is that if we pick up a sample point small omega from the complementary of that event, then x n does not match with the truncated random variable must happen finitely often only, and since it happens finitely often, then after a certain stage the equality starts occurring. So, that is what we are writing down here. So, the observation says on the complement of that appropriate null set, we must have x n matching with the truncated random variable, but for each omega we must have a certain number capital N depending on omega, maybe that after that stage onwards we have the equality. All right. But then if that happens, then immediately we observe that on that complementary event the convergence of this series means the truncated series also converges, because we can simply ignore first capital N minus 1 many terms, and therefore, we end up having the equivalence of these two series. So, as long as we ignore the first capital N minus 1 many terms, then the convergence of the first series is equivalent to the convergence of the second series. But now, let us look at the second series here. It is formed by this truncated random variables, which are of course functions of the original random variables, and therefore, they are still independent, they are in L2, and moreover by our assumption what we have is that their expectation series converges as well as the variance of the truncated random variables converges. So, therefore, the truncated random variable, if we construct the series, they must converge. This is simply by the corollary 1, which was the 2 series theorem. So, therefore, since this converges almost surely, we are going to have again a measure 0 set, which we denote by B, such that on the complement of the measure 0 set this series converges. All right. But now, let us look at this measure 0 set, which is formed by these two null sets A and B. So, look at A union B. So, that probability is 0, and on the complement of that null set, which is the intersection of this A complement and B complement, there what happens is that we end up having the convergence of the original sequence of random variables, but pointwise. But since this is happening on the complement of a measure 0 set, we end up having the required almost sure convergence that we stated as part of the theorem. So, therefore, if these 3 series converges for some C positive, then the original sequence of random variables must converge almost surely. Here you note that we have dropped the assumption of integrabilities and are using the conditions in terms of the truncated random variables. So, let us see the application of this result. So, here what we observe is that we now work with a number p between 0 and 1 and look at x n's, which are now IID, and having this distribution that it takes the value plus 1 with probability p minus 1 with probability 1 minus p. Again we can think of coin which has probability p of having a head if we toss it once, and if we repeat the tossing, then whenever head appears we will take the value plus 1, otherwise we will take the value minus 1. Then that is going to give you this sequence of IID random variables, and corresponding to that we now look at a generalization of example 1 that we considered earlier. So, we again look at x n over n and call it y n. Now, we want to check when the series formed by y n converges almost surely. So, by the necessity part of this theorem, in particular the truncated random variables with the truncation constant by 1, that expectation for series must converge. Now, you note that the random variables x n's are taking value plus minus 1, and therefore, y n's are also taking values within minus 1 to plus 1, because as long as you divide by n, the values are between minus 1 and plus 1. So, here what is happening is that the y truncated at 1, that is nothing but the original random variable itself, right, because we are truncating by 1 and all the values of y n are between minus 1 plus 1. So, therefore, this equality occurs, but then put in the definition of y n, which will give us 1 by n times expected value of x n. But this is immediately clear that this value is 1 over n times 2 p minus 1. So, therefore, for the convergence of this series we must have 2 p minus 1 equal to 0, because as long as 2 p minus 1 is non-zero, we are ending up with this divergent series which is exactly equal to this quantity. So, therefore, for the convergence of this truncated expectations, this to happen we must have 2 p minus 1 equal to 0, which tells you p must be equal to half. So, this is a necessary condition for the series summation y n to converge almost surely. But on the other hand, in example 1 we had shown that if p equals to half, then we will end up with the almost sure convergence of summation y n, which is x n over n. So, therefore, what we have ended up proving by using that 3 series theorem now is that in this specific example the summation x n over n that converges almost surely if and only if p is equal to half. And as discussed earlier, you can also generalize this thing in this exercise, that if you have a sequence of real numbers such that the corresponding series is square summable, then continue with x n as above, then try to figure out some condition in terms of this parameter p, which will ensure the almost sure convergence of summation x n times a n. So, we are scaling this by this numbers a n. So, now in this lecture we have looked at sequences of independent random variables and looked at certain additional assumptions which will ensure the almost sure convergence of this series of random variables. Now, till this lecture where we have looked at this convergence of series or sequences of random variables, there we had looked at very nice conditions which will ensure various modes of convergences. Now, we are going to see applications of these results with the next lectures. We stop here. Thank you.